So in this video, we're going to start talking a little bit of probability, the basic probability setting, and some basic counting techniques that's going to show up. So I want to start saying that everybody has some experience with some basic probability, and we know basic examples like the ones here. Like if you flip a fair coin, what is the probability that it lands tails, right? It's 1/2. If you roll a fair six-sided die, what is the probability that it lands on the 4, right? Now, a key point here on both of these scenarios is that it's a fair, right? I'm saying it's a fair coin. I'm saying it's a fair six-sided die. So this is a very basic probability, like a concept that everybody has from common knowledge, from even if not from school. The basic probability principle, I'm going to call it, is if an experiment has n outcomes and each one of them has the same chance of happening, they're equally likely to happen, then the probability of one outcome is just 1/n. There's a few words here that I haven't defined. What's an outcome? What's an experiment? So my first example, flipping a coin, is experiment. Yeah. In my second example, rolling a die is experiment. The outcome was, in the first example, one outcome could be you get heads or you get tails. In my second example, an outcome, you can get any number between 1 and 6, right? So the probability of those is 1/n. That's a very basic probability. Now let's do a little bit more interesting. Now I'm going to roll a pair of dice. And what is the probability that you get an 8? So now it's a bit more complicated because I have 2 dice. And each one can land any of 2 numbers between 1 and 6. And there are a few ways of how I can get an 8. Right? So now it's a little bit more complicated to count, and that's why we have to learn how to do some count techniques. This one is not at the core of those techniques, but this one is still pretty basic, but it has a little bit of a setup. So the way I like to set this up is I'm going to distinguish between the 2 dice. I'm going to say I have 1 die with yellow that can land any number between 1, 2, 3, 4, 5, and 6. Then I have another die that I'm going to do with my orange that can also land any number between 1, 2, 3, 4, 5, and 6. So I'm gonna draw a grid here, and my grid is going to represent every little square in my grid is going to represent one possible outcome of this experiment. So my experiment here is rolling a pair of dice, and the yellow die could have landed in any number between 1 and 6. And orange dice could have landed any number between 1 and 6. So, for example, this number right here, this one would mean if it lands here, that means that the sum is a 6, but I got that 6 by getting the yellow die on the 5 and the orange die on the 1. There's another one symmetrical over here, right, where I also get a 6, but it's the yellow one that is in the 1 and the orange one in the 5. So keeping these organized help you see that there are 2 outcomes, 2 possible ways you can get a 6, even with a 1 and a 5. Another interesting thing about this sketch is that how you get all 6s would be in this diagonal, right? Or this, not diagonal, but this line across. Because if you decrease the yellow value by 1 from 5 to 4, in order to get a 6, you have to increase the orange value by 1 to get to 2, right? So you're moving in this 1 down, 1 over, and you still have the same sum. So a very easy thing here to notice is that maybe you didn't think about this, is that the most common thing to show up, or the one that has more likely to happen when you roll a pair of dice, is to get a 7. Why? Because that is this main diagonal, right? That's the way you can get a 7, and every diagonal here would have the constant sum, so those are all the ways you can get a 7. That's why many of these board games have something special happens when you get a 7, because they expect that to happen the most. So my question was, I got distracted. What is the probability that you get an 8? So an 8, I can get it. That's a 7. So I was almost there. To get an 8, it's the next line here, right? The 6 and the 2 is an 8. The 5 and the 3. The double 4, look, that's only one way I get a double 4, right? Then the 3 and the 5 and the 2 and the 6. So I have 1, 2, 3, 4, 5 ways I can get an 8. But what's the denominator? The denominator is, well, I need to fill all these squares. how many of each one of these squares is one possible way it could happen. It's a grid of 6 by 6, so it's 36. So there is a 36. So that's a probability of getting an 8. There's 5 possible ways I can do it out of 36. Now I'm using something not my basic. In my basic one and before, I only had it with a 1 up there, but we're gonna set this up, right? It's a bit more complicated. But you can count the number of favorable outcomes of what you want divided by the number of total outcomes. So this basic probability notion will not take us too far. We're gonna need to learn more techniques. I put a few things that we need to learn why we can go dive deeper into probability. What happens if not all outcomes are equally likely to happen? For example, in my example before, if I asked you, what's the probability that you get an 8, which is versus what is the probability that you get a 7? It's not the same, right? The 7 would have been 6 over 36. So the 7 would have been 6 over 36. So you have to count differently, so it's not a little bit simple. How can we handle experiments with complex mix of outcomes? For example, at the end of our study, we're going to learn how can I find a probability when we give 5 cards in a regular poker game, so I give you 5 cards. What is the probability that I just gave you 2 pairs? And in a poker game, I gave you 5 cards. What is the probability that I gave you 2 pairs? So there's a lot more counting there that we need to do that we don't know yet. Okay, we have to explore that. And what do we do if we repeat experiments back to back or back to back to back? For example, if I flip a coin 10 times, what is the probability that we get at least 4 tails? Yeah, so that's the kind of questions we want to answer with learning, diving deeper into probability. So everybody knows this basic probability. It's have an intuition of what it means, but we need to dive deeper into what that means. Okay, now some definitions of probability. So we already used a few of these, but this is the language we're going to use when we talk about probability. So an experiment is just anything we're talking about for which specific results are obtained. It could be flipping a coin, it could be rolling a die, it could be selecting a person at random from a group of people, anything like that. An outcome is a result of a single trial of a probability experiment. I select one person from a group, or I flip a coin. It could be flip a coin 3 times. Yeah, that's an experiment. The collection of all possible outcomes is called the sample space. For example, in this example here, my sample space was all possible ways, so they're represented by those 36 squares in my grid. The event is a collection of outcomes. An event can consist of one or more outcomes. A simple event only has one outcome. For example, in my rolling a pair of dice example, obtaining an 8 is an event because it has 5, 5 possible. It's an event has 5 outcomes. Yeah. So a simple event would be, what's the probability that you get double 4? That's only one outcome. So an example, another one is rolling one die. That's easier. With one die, an outcome is you get a 4. The sample space is any number between 1 and 6, and an event is roll an even number, right? It could be 2, 4, or 6 if you roll just one die. We're going to use those terms as in this lesson, so it's important that we just have a basic understanding of what they are whenever we use them again. So now let's go a little bit a more interesting problem. Pretend you at your work, you have a cafeteria, or out for a conference, and it gives you 2 options for salads, 3 options for main courses, and 3 options for dessert. You're given a tray with one random selection of each: a salad, a main course, and a dessert. What is the probability that you get to your preferred selection? So you wanted the Caesar salad, you wanted the turkey sandwich, and you wanted the cheesecake. You know what you get. What's the chance that you really get that, exactly what you wanted? So this is a little more complicated, right? We need to know how to count these things, and this is what we're going to do. So we're going to assume first that all outcomes are equally likely. So it's equally likely that you would get any of the options for salads, any of the main course, or any of the desserts. If you know how many outcomes were possible, then it's going to be it's one preferred, the one you want, divided by the total number, right? The problem is how many outcomes are possible. So I'm going to go back to this slide to make I'm going to call this a tree diagram. So I'm going to say I have 2 options for salads. So I'm going to put like salad, put green salad and Caesar salad, okay? Then I'm going to represent the 3 main courses. I'm just going to write like main dish 1, main dish 2, main dish 3, and then I'm going to have a main 1, main 2, and main 3 for the Caesar salad. And now I'm going to connect them with a line. This is going to be like a tree diagram. And now my last thing is the desserts, where I'm going to do, I have 3 desserts. So I'm going to write, this is going to be weird, D1, D2, and D3. And I have to do that several times. So I'm going to copy it and paste it. It's going to be hard to fit all these here. I hope I can. I'll resize it in a minute. Okay, so let me resize this. This is getting too big. So that's the magic of doing this in these electronic devices. I can shrink everything. But now in particular, I want to shrink these guys. I think those are the ones I want to shrink, not these probably. Yeah, so I'm going to put these here, these there, and these there. Perfect. And I'm going to resize this and make it bigger. And shrink these. In fact, I can probably just delete this one and use these. Okay, so now I'm going to have lines connected like this. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3. I hope you understand what this represents. So every one of these in the bottom. Oops, that was not the one I wanted. Let me use this one. Can I see this one? Yeah. So every one of these in the bottom represents one selection. Yeah, at the very end. So this means I thought I got the 3rd dessert with the 3rd option of the main with the green salad. Right. Well, this one would mean I got the 2nd option for dessert with the 1st one of the main with the Caesar salad. Correct? So how many outputs do I have? All I have to do is count how many do I have at this level. Right? Because each one at this level represents a different selection. Right? 1 dessert, 1 main, 1 salad. So I have to count here, and it's 9 on that side and 9 on that side, so there's 18. Now, how did I get the 18 easily? Well, if you think about it, we're never going to do it. This is called a tree diagram. We're never going to have to do a tree diagram again if we learn how we just count this quickly. All I have to think about is I have 3 spots to make my meal. The first one is to get the salad. The second is to get the main. The third one is to get the dessert. And then you have to do is the options. How many options do I have for the dessert? Sorry, for the salad, 2 options. How many do I have for the main? 3 options. How many do I have for the dessert? 3 options. So all I'm doing is multiplying those numbers, and that's how you get the 18. Yeah, because this tree diagram, at the end, you just go 2 salads, 3, you multiply 2 times 3, you get the 6. Then you multiply that by 3 to get the 18. Yeah. So my answer is 1 and 18. Now the probability that you get what you wanted, if everything was equally likely, it's 1 and 18. So this is called the fundamental counting principle. It means if one event can occur in m ways and the second one can occur in n ways, the number of ways the 2 can occur in a sequence is m times n. And this is the interpretation, okay? Like this means the first is you get one of the 2 options for the salad. The next one is one of the 3 options for your main course and so on. So you can repeat this as many times as needed. You just multiply them. So let's do some examples here. How many different license plates can be made using 3 letters and 3 one-digit numbers? 3 letters and 3 one-digit numbers. So this is the same principle as we just did. So I'm going to have 1, 2, 3, 4, 5, 6, right? 3 letters. If I'm assuming that the letters, they're license plates. So you know the license plates they're not upper and lowercase, they're just all uppercases. So there's 26 letters in the alphabet in English. So I have 26 options for these letters. And then one-digit numbers, one digits go from 0 to 9, so they are 10 options, right? So there's 10 options here, 10 here, 10 here. So there's no way I'm going to do a tree diagram here, but that's the same logic, right? You would have your alphabet to pick the first letter. Once you pick the first letter, you would do a branch for all 26 letters for your second one, right? So that's a lot of leaves on this tree. So you don't need to do it, but the logic is the same as in the meals in the tray of the cafeteria. So you just multiply 26 times 26 times 26 times 10 times 10 times 10. If you wonder what that is, you can grab a calculator here. I'm using the Desmos calculator, and I'm just going to go and do 26 to the power of 3, then times 10 to the power of 3, which is 1,000, right? I'll need to type that 3 times. So 17 million and a half possible license plates. Second question says, how many access codes of length 5 can be created using the keypad that has only 5 buttons? So pretend there's like a keypad in a lock that has only 5 buttons, and you want something created for 5. So this is the 5 shows up twice, but this is it's the same setting. Now you have 5 slots to fill with 5 options each, because the 5 comes from here, the length 5, but then you have 5 buttons, so there's 5 for that. So it's 5 to the 5. And you multiply those numbers. Sorry, I didn't write that number here. This number was 17,576,000. And this number is going to be 5 to the power of 5 is 3 to 125. Okay, now the last question here says, how many passwords can be created with 8 entries, each being a letter or a 1-digit number? So now we want to create a password. When you tell you to update your password, and how many passwords are they? Why do you need to worry about it? What's the order of magnitude of creating passwords? So again, I'm not differentiating if they're uppercase or lowercase. So they just use uppercase. So if each entry can be either a letter or a number, then there's 36 options, right? 26 for the letters plus 10 of the numbers. So I have 1, 2, 3, 4, 5, 6, 7, 8. Each one could be 36 options. Why 36? Each one could be either a letter, there's 26 of them, or a 1-digit number. Between 0 and 9, there are 10 numbers, so it's 36. So I'm not going to bother this. It's 36 times 36 and 36. Of course, that's just 36 to the 8, right? So it's a huge number. Oops, sorry, not there. 36 to the power of 8 is huge. So this is 2.8 times 10 to the 12. Okay. So you have to understand what that means. That's this calculator types it correctly times 10 to the 12. Some calculators are going to spit out with an E12. Understand that that's scientific notation, and this is what we're doing this right now. Okay, I'm going to stop this video here and start the next one in a minute.